Hi everybody, and welcome to part 4 of our notes for this unit. This is the last part of notes for this unit, so let's go on ahead. We're going to focus on an area of chemistry known as spectroscopy and talk about light and waves in this particular part of the notes. All right, so I'm going to read a little bit. Atoms have the ability to absorb energy, all right? And anytime we're talking about energy that's being absorbed or given off, it's known as EMR, electromagnetic radiation, all right? So there's lots of different ways to excite atoms to allow them to absorb energy. You can add electricity to them. You can add energy to them. You can burn them, which is what we're going to be doing in our lab. Okay. These atoms are considered excited when their electrons have moved from their ground state, that is their normal electron configuration. Some of those electrons actually jump up to higher states, and we say that the atom is then excited. Well, the atom's not going to stay excited for that entire time. It's just going to stay excited for a split second. The electron will then fall back to its original energy level. That energy has to go somewhere, and it's actually given off in a wavelength that for a lot of elements we can actually see. So it's given off in a type of light that is visible to us. All right. This process can be used to actually identify many chemical substances, and that is known as spectroscopy. All right, let's show just kind of what that's going to look like for you. All right, so here we go. Here are what we call the spectrums for several different elements. Here's hydrogen spectrum. I won't go too close because it'll get blurry. All right, and you can look at these in your textbook too. There's sodiums. We have helium, neon, mercury. And what elements do actually is once you've excited them and then they fall back, they give these patterns that are very much, they look a lot like a barcode, but they're very much like a fingerprint for the element. And they can help in identifying, if you have an unknown substance, what that is made of. You're going to be doing or watching the flame test where we're going to see these atoms. We're going to excite them and see what kind of colors they give off. All right. So right here, you notice that these colors are in different wavelengths. We're going to talk a little bit about that. All right. And we're going to talk about 3 important characteristics of waves, because this again helps us understand the study of spectroscopy. All right, first thing you have to understand is what a wavelength is. And a wavelength is just that. It's simply the length of the wave. All right, the distance is typically from one peak or crest of the wave to the next. Wavelength gets the abbreviation lambda, which looks kind of like an upside down Y. All right, some people think it looks like a wishbone. All right, it's usually measured in some type of meter. Okay, but it can be in centimeters and it will often be in nanometers. And this is one that you're not required to memorize. We'll always give you this conversion, but 1 nanometer is 10 to the negative 9th meters. So that's one. Definitely put a star by that in your notes because you're going to be using that. Okay, and again, wavelength gets the abbreviation lambda. All right, the next characteristic of a wave that you need to be familiar with is that of frequency. And frequency gets this little abbreviation. It's like a cursive V. It's the new symbol, so a cursive V. Frequency is how many waves pass a certain point per second. So it's how often something occurs. It's a cycle per second. And that is called a hertz. All right. So 1 cycle per second is known as 1 hertz. A hertz is also second to the negative 1. All right, so those are interchangeable. Okay, so let's look at the relationship between wavelength and frequency. Before that, let's talk about speed, because we have to talk about how fast these light waves are going. In a vacuum, which just means for our purposes, if everything's perfect, electromagnetic radiation travels at a speed of 3.0 times 10 to the 8th meters per second. That is the speed of light. That's actually a good value to memorize just for any science classes you're going to be taking. All right. Because all of these waves we're considering are in perfect condition. Okay. They're all traveling at the speed of light. As their wavelength increases, their frequency will go down because speed of light never changes. So this right here gets the big star as far as the equation we're going to be starting with today. C is equal to lambda nu. Speed of light is equal to wavelength times frequency. All right. So as we can see here, Okay, look at my first example. I have a short wavelength, but in the same amount of time, I get a lot more waves. Short wavelength, high frequency. As one goes up, the other goes down. Here, I have a much larger wavelength, but the waves don't occur as much. All right, so as one goes up, the other goes down. Okay, so let's see this equation in action. All right, and I'm going to show you our first one, and then you can do the others on your own. What is remember, lambda is wavelength. What is the wavelength of a wave with a frequency of 4.86 times 10 to the 15th hertz? Here's my original equation. C is equal to lambda nu. I'm solving for nu. All right, so what did I do? I divided each side by frequency. So wavelength is equal to the speed of light over frequency. My speed of light never changes, okay? It's 3 times 10 to the 8th meters per second over the hertz I gave you in the problem, which remember is per second. So your seconds divide out, and then you're left with a length measurement, which is absolutely what you should be left with. And it should be about 6.17 times 10 to the negative 8th. Now, as far as significant figures, I don't want you to stress over them. Just look at this number here. It has 3 significant figures. A great idea is let's round your answer to have 3 significant figures as well. All right, so let's take a look at this electromagnetic spectrum, and this is kind of a cute little picture of it, and just to talk about what the relationship is and the different types of waves that we've got going on here. All right, right in this tiny little part right here, I don't know if you can see that word says visible, that's the only part of the electromagnetic spectrum that we can actually see. That's our visible light, that Roy G. Biv you might have learned about when you were in elementary school. All right, as we move over here, we start getting things like X-rays and gamma rays. All right, we're ultraviolet right here. As we move over to my left here, this is more infrared, and we're moving to radio waves, all right, that allow us to have television and all of that good stuff, okay? All right, do I have another one? Here we go. Here's a little bit more simple one to look at without all of the graphics. And again, this one's flipped actually, so it doesn't matter as long as the numbers line up. Here's my visible, here's my UV, X-rays, my gamma rays. Then I'm moving over to microwaves over here, your long and short radio waves. What I want you to notice is over in this area where they're the things that we tend to know aren't great for us, things like UV, ultraviolet radiation, X-rays, gamma rays. What you're getting there are waves that have a very high frequency and a very short wavelength. All right, as we move over to things that we certainly hope are not too bad for us since we have radio waves going on all the time. All right, what you're dealing with here is a much longer wavelength, all right, and a much smaller frequency. Okay, so go on ahead and solve this next one. What is the frequency and type of energy of a wave with a wavelength, remember that means wavelength, of 2 times 10 to the negative 4th? Pause the video and see what you get. All right, fantastic. So I did my math here, and again, I had a number with 2 significant figures, so I give my answer in 2, and I get about 1.5 times 10 to the 12th hertz. So I'm gonna go up here, and what you really wanna look at is just that exponent when you're looking at any of these charts or graphs from your textbook. So 10 to the 12th hertz, here are my hertz. So if I'm at 10 to the 12th, right there, I'm in infrared. Okay, so that's infrared radiation right there. All right, our last topic is what's known as Planck's hypothesis. All right, and what Planck said is that energy is quantized. What that means is energy, what he said, is given off in little packets called quanta. You might have heard them also referred to as photons. Another scientist by the name of Einstein coined the term photon, so it tended to become a little bit more popular. And the energy of a wavelength was related to its frequency. So this is our second big equation for today. It's known as Planck's equation. E is for energy. H is what's known as Planck's constant, always going to be given to you. You never want to memorize that. And then there's our nu, there's our frequency. All right, so this just shows as frequency goes up, my energy is going to go up. Planck's constant is 6.6 times 10 to the negative 34th joules per hertz. Not a number to worry about memorizing. I would always give you that number, but certainly start in your notes so you have it. All right, and as we mentioned before, the higher the frequency, the greater the energy. All right, since wavelength and frequency are inversely proportional, the longer the wavelength, the lower the energy. All right, so we're relating energy directly to frequency, and we know that frequency is related to wavelength. Okay, so let's look at, here we go. So calculate the energy of a photon, which just means a wave, a packet of energy, with a frequency of 3 times 10 to the 13th. So there's my Planck's equation. E is equal to Planck's constant times frequency. I'm going to go ahead and plug those numbers in. I have 6.6 times 10 to the negative 34th joules per hertz times 3 times 10 to the 13th hertz. The hertz divide out. We're left with joules. All right, well, great. Joules is an energy measurement, so that's exactly what you want. So your answer should be about 2.0 times 10 to the negative 20th joules. All right, fantastic. So let's go on ahead. Feel free to pause here if you'd like to. All right, so calculate the energy of a photon with a wavelength of 6 times 10 to the negative 11th. All right, so in this question, you're not dealing with the frequency directly, you're dealing with the wavelength. So what I decided to do is I solved for frequency using my speed of light equation. I end up getting my frequency, I plug frequency into my Planck's equation, and I get about 3.3 times 10 to the negative 15th joules. All right, great. Okay. All right, so that ends our notes. As I said, you guys are going to be doing the flame test lab, and you'll be showing me some of these equations, so please make sure you refer back to them. All right, take care.